Good morning. My name is Alan Halakmi. I'm a Senior Manager of Solutions Architecture at AWS. Welcome to this session on Advanced Architectures with AWS Transit Gateway. The session will provide you with the fundamental architectural and functional knowledge that you'll need to build advanced architectures with the AWS Transit Gateway, and I'll start calling it TGW just for convenience. I won't be spending time in the console or showing you click-by-click walkthrough configuration. Rather, this session is designed to share key concepts that allow you to leverage the robust capabilities of the TGW. The session will start with at a modest pace, covering the basic components and operation of the TGW. However, the session will accelerate quickly into advanced use cases and assumes an intermediate to advanced level of IP networking knowledge. A final note before we get going. While you can implement the architecture shown, you should consult with a solutions architect to make sure that it's the most appropriate solution for your given need. So let's get right into it. Customers tell us they want robust networking capabilities that allow simple, seamless, and global connectivity between their AWS cloud environments and their on-premises environments. But we also heard from customers that they were running into challenges. They wanted an easier way to manage point-to-point connectivity at scale. They wanted more bandwidth for their VPCs, and they wanted a centralized place to manage routing within, into, and out of the AWS cloud. Let's take a look at AWS networking before the introduction of the Transit Gateway. A customer would build a VPC and then another. And they would want to connect those two together. And we can do that. We have VPC peering. But what happens when I add the next two VPCs? Well, I can peer those. But as you know, VPCs are not a transitive point for packet routing. So for all of these VPCs to talk to one another, they need to be fully meshed. VPC peering is okay for 4 or 5 or 6 or 7 VPCs. But what happens at scale? Here's the formula for calculating the number of peering connections required for a full mesh VPC infrastructure. Let's say that I have 10 VPCs. Do the maths. That's 45 peering connections. So at least 45 API calls for peering, plus API calls into each of the VPCs to update route tables to point to the peers. All right? So you can automate that fairly simply, but what happens when you have 100 VPCs? That's 4,500 peers. That starts to become complex to manage. Moreover, VPC route tables support up to 1,000 static routes and up to 125 peers. So a full mesh of 100 VPCs will create a challenge. But customers told us we could also help them in other places. So this is the diagram that we had. But what about edge connectivity when you want to connect your on-premises infrastructure? Well, when using AWS site-to-site VPN, you create a customer gateway, then you define a VPN connection between that customer gateway and a virtual private gateway that's attached to your VPC. And then you need to go through that process for each VPC that you want to connect. Similarly, with AWS Direct Connect, you create a private virtual interface, or VIF, for each of the VPC virtual private gateways that you want to connect to. So we simplified this with AWS Direct Connect a bit ago by creating something called the Direct Connect Gateway. And that allows you to connect multiple private VIFs and virtual private gateways together with a single global network object. With this picture as background, we set off to provide our customers with something simple to use that's scaled to thousands of networks. Enter AWS Transit Gateway, a network transit hub that you can use to interconnect your VPCs and on-premises networks. Now, when you want to connect those VPCs, you simply attach them to a TGW. When you need access over VPN, you can attach that AWS site-to-site VPN to your TGW. And newly announced in April, you can now attach Direct Connect gateways to TGWs created in US regions excluding GovCloud. Let's run down the anatomy of a TGW. Resource attachments are the logical connections made to the TGW. They are both a source of and destination for packets. Today, TGW supports 3 attachment types: Amazon VPC, AWS Site-to-Site VPN, and AWS Direct Connect Gateway. Many of you connect AWS Client VPN to the TGW today using the VPC attachment. Our roadmap includes the ability to connect the AWS Client VPN directly to the TGW. A moment ago, I mentioned that we recently launched Direct Connect Gateway support for the TGW. So I just want to take a brief interlude here to explain how that works. So first, we introduced a new VIF type, a transit VIF. So now you can have 51 virtual interfaces on your Direct Connect connection. You can have 1 transit VIF and 50 VIFs that are mixed between public VIF that provide access to AWS public services using public IPs, and private VIFs that provide access to Amazon VPCs using private IP addresses. So let's see how a typical configuration with Direct Connect Gateway and virtual private gateways works versus the integration with Transit Gateway. So I have my on-premises environment, and I have a Direct Connect Gateway location. I have a Direct Connect location. I provision a connection between the two of them, and I create a private virtual interface. That private virtual interface is subsequently attached to a Direct Connect Gateway. And then for the VPCs that I want to have access to my on-premises environment, I associate the virtual private gateways of those VPCs to the Direct Connect Gateway. Now let's see how this works with the Transit Gateway. So let's create a Transit Gateway, provision our single Transit VIF on that connection, attach that Transit VIF to the Direct Connect Gateway. Yeah, as shown, this doesn't work. Let me explain why. Direct Connect Gateway will support either private virtual interfaces and virtual private gateways, or transit virtual interfaces and transit gateways. You can't mix the two of them on a single Direct Connect Gateway. So let's create a new Direct Connect Gateway, attach the transit VIF to it. In the Direct Connect console or using the APIs, you can attach the transit gateway to the Direct Connect Gateway, identify routes to originate, and you can also then attach the transit gateway to the VPC. Some other things to note about the Direct Connect Gateway integration. Jumbo frames over the transit VIF are 8500 for the MTU. A Direct Connect Gateway can support up to 3 transit gateways. Conversely, a transit gateway can support up to 20 Direct Connect gateways. For each transit gateway, you can originate up to 20 routes towards the on-premises environment. And a last note that I should make about Direct Connect in general, whether you're using the transit VIF or a private VIF, or even if you're using our public VIF for accessing public services like S3 and DynamoDB, think about redundancy. You should certainly be provisioning a second connection to another AWS Direct Connect location to provide the redundancy for your infrastructure. Okay, back to the TGW anatomy lesson. We talked about our attachment types. Now let's talk about TGW route tables. Route tables in the TGW allow you to create routing domains similar to virtual routing and forwarding in the typical network world, or VRFs. In a typical configuration, when you generate or when you create your transit gateway, you also get a default TGW route table. Route table associations are used to make next hop routing decisions for packets received from an attachment by the TGW. Each attachment can have a single route table association. Oftentimes, this association is with the default TGW route table. Route propagation allows you to define which of the TGW route tables will learn routes from the resource attachments. You can propagate to 0, 1, or many TGW route tables. So here's the route table for our diagram. I've added a static default route at the top, and we'll talk a little bit more about that later. But I've also added propagated routes for .1, 10.1, 10.2, and 10.3. And they're propagated via their respective attachments from the VPC, site-to-site VPN, and Direct Connect Gateway. You can specify whether to automatically associate with and propagate to the TGW's default route table at the time that you create your TGW. These features enable you to exert as much or as little control on attachments and TGW routing as is appropriate for your particular environment. So now we have a complete TGW configuration, but we still have work to do on the edges. We've defined the route table in the TGW, but the edge resources still need to understand how to get to the TGW from a routing perspective. So let's talk about how routes are learned both by the TGW and by the attachments. In the case of a VPC, you have two options. The VPC will automatically propagate to the route tables that you specify in your TGW, or you can statically define a route entry in the appropriate TGW route table. In the case of AWS site-to-site VPN, we offer two configuration modes. In static mode, you'll need to specify a static configuration in the appropriate TGW route tables. If you're using the dynamic mode of AWS site-to-site VPN, routes are propagated over BGP, and you can select which route tables receive that propagation, or, in addition, you can select to input a static route entry. In the case of Direct Connect, it's the same case. You can statically define a route, or you can take the BGP propagated routes from the Direct Connect Gateway and specify the route tables that will receive them in the Transit Gateway. So that's how the Transit Gateway route table gets its routing information. Now I want to talk about how the edges, these attachments, how they get routes to the TGW. In the case of the static AWS site-to-site VPN configuration, your customer gateway will need to have a static route that points towards the TGW. In the case of the dynamic configuration, BGP will propagate the routes in the associated route table to the customer gateway. In the case of the Direct Connect Gateway, at the time that you associate your transit gateway, you are allowed to provide up to 20 routes to originate towards your on-premises environment. These routes do not have to have anything to do with the contents of the route table. You are able to statically define the routing prefixes that will be originated and then transmitted by Direct Connect Gateway to your on-premises equipment over BGP. In the case of VPC, you'll need to statically define the path to the TGW in the VPC route table. So to give you a sense of what that looks like, I have a VPC on the left and on the right. I have a transit gateway in the middle that's receiving propagated routes from those VPC attachments. In order for the VPC on the left and right to communicate, a static entry is entered on both of them, pointing to the transit gateway. The transit gateway has next hop information to forward the packet. This is what a default configuration might look like. All of the attachments are associated to a single TGW route table. All the attachments are propagating to that same default route table. And you'll note that although I have 4 attachments, I only have 3 entries in the route table. The on-premises environment is using Direct Connect as a primary connectivity point and a dynamic AWS site-to-site VPN configuration as a backup. In this case, the Direct Connect Gateway route advertisement is what is installed in the route table, which brings us to the question of how do we select best path? So here's the path selection behavior. First, longest prefix match. The second is static route entries, including site-to-site VPN. If you're using the static capability or the static configuration for site-to-site VPN, that static route is preferred over dynamic routes. This distinction is important because it's a slight difference in the behavior from the virtual private gateway. After static routes, VPC propagated routes are prioritized, then Direct Connect Gateway, and then dynamically received AWS site-to-site VPN routes. All right, I'm going to go into 2 common use cases, 3 advanced use cases, and then a customer pattern that we're seeing start to repeat. As we look at the specific use cases, I'll walk through the configuration of each of them first, and then I will verbalize a packet walkthrough and highlight a bit on the screen. As I mentioned previously, this is going to get deep fairly quickly, so if you need to come back to this on YouTube, feel free to. All right, let's start with the first of our common use cases, a flat network. So I have a VPC 10.1/16. It has an attachment with the Transit Gateway. It is associated with the default route table. The VPC route table has a 10/8 route pointing to the Transit Gateway attachment. And the Transit Gateway is propagating the VPC attachment route into the default route table. I can add a 10.2, 10.3, and 10.4 VPC, each of them configured identically, propagating into the default route table, associated with the default route table, and in this case attached to the same Transit Gateway. So in this scenario, if I want an instance at 10.1.0.10 to talk to an instance at 10.2.0.20, the 10.1.0.10 instance will put its packet out to the default gateway in its local subnet. That default gateway is the implicit router for the VPC. The VPC will then do a lookup, or the implicit router will do a lookup in the route table associated with that subnet in the 10.1 VPC and find a route for 10/8 with the next hop of the TGW. The packet is forwarded through the attachment to the Transit Gateway. The Transit Gateway does a lookup in the route table associated with the attachment. In this case, we only have one route table. It identifies a route entry for 10.2/16 with the next hop of the attachment for VPC2, and the packet is delivered. In this configuration, which is the default configuration, you have full connectivity between your VPCs. Now, a word of note, because I know my terminology is going to bounce moving forward. When I say route domain, or when the slides say route domain, that means a route table inside of the Transit Gateway. Okay, let's look at another common use case. So similar to the one that we just saw, so I have VPCs 10.1 through 10.4/16. They are associated with the routing domain for VPCs. They're attached to a common Transit Gateway, and each of them have a VPC route table that has a default gateway pointing to the attachment for the TGW. In this case, we're going to add a VPN attachment. That VPN attachment will be associated with a different TGW route table. We'll call this the routing domain for VPN. The VPN will advertise a default route. We will propagate that default route into the routing domain for the VPCs, and we will propagate the CIDRs for the attached VPCs into the routing domain for the VPN. So now let's say that I want to send a packet to an on-premises piece of gear, 172.16.1.1. So I have my instance 10.1.0.1. It puts the packet out on the network. It goes to the gateway in the VPC. The implicit router picks that up, does a lookup in the VPC route table associated with that subnet. It finds a default route pointing to the Transit Gateway attachment. The packet is transmitted to the Transit Gateway. When the Transit Gateway receives the packet, it does a route table lookup in the table associated with the attachment for VPC 10.1/16. That route table has a default route pointing to the VPC attachment, and the packet is forwarded down the VPN. Now, when 172.16.1.1 wants to reply back to 10.1.0.10, it sends this packet through the local infrastructure, it comes through the VPN, and is received by the TGW. The TGW does a route table lookup in the route table associated with this attachment, which is a routing domain for VPC. It finds an entry for 10.1/16 with the next hop of the attachment for VPC1, and the packet is delivered to VPC1. Note that in this configuration, there's no east-west connectivity within AWS between these VPCs. However, there is full connectivity between the VPCs and the on-premises environment. And a footnote, and something that I'll review a little bit later, there is nothing that prevents, unless you prevent it, a hairpin turn through the VPN customer gateway. So just be advised of that. But within AWS, there's no direct connectivity between these VPCs. Let's look at some advanced use cases. One is a centralized NAT. So in the configuration here, we have VPC A 10.1/16, VPC B 10.2/16. Each of them has an attachment to a TGW. They're associated with the VPC route domain. Each of them has a VPC route table pointing their default route to the TGW. On the right side, we have an outbound VPC. That outbound VPC is connected or is attached to the TGW. And you may not be able to see it too well on the screen, but within the outbound VPC, there are some lines. The horizontal slivers indicate availability zones, and the vertical slivers indicate subnets. So why have I put the attachment in a separate subnet from this source NAT device or NAT gateway? We want the NAT device to be in what we call a public subnet. As you can see from the route table in the top right, it has a default gateway pointing to the internet via an internet gateway. It has a route for 10/8 that points back to the attachments for the TGW. But if we put the transit gateway's attachment in its own subnet, it has the effect of allowing us to define an ingress route table. So what happens here is I can define subnet route tables for each of the availability zones where the transit gateway attachments exist, and I'll define a default route that matches the specific NAT instance or NAT gateway in the same availability zone. So in fact, this VPC has 4 route tables. It has one route table for the public subnets, and it has 3 individual route tables for the attachment transit subnets. So let's see what a packet flow through this might look like. So if I have an instance 10.2.0.20 that wants to communicate out to a node on the internet, 10.2.0.20 will create the packet, deliver it to the local gateway. The VPC implicit router will do a lookup in the route table associated with that subnet. The VPC route table says that the next hop is the transit gateway. The packet is forwarded through the attachment. Then the TGW does a lookup in the route table associated with that attachment and finds a default route pointing to the outbound VPC attachments. The packet is delivered to the outbound VPC attachment. The outbound VPC attachment then delivers it, because it's not in the local subnet, to the default gateway for that subnet, which causes the VPC to do a lookup in the subnet route table. The next hop address for default route is the specific NAT gateway or NAT instance for that availability zone, and the packet is forwarded on. Once that NAT instance does its source NAT, the packet's put out to the implicit router. In this case, the packet's forwarded onto the internet gateway and onto the internet. When the packet's returned, it's received by the NAT device that corrects the destination address. It sends that information, the 10.20.0.2 packet, to the transit gateway. When the packet's received by the transit gateway, a route table lookup is done in the associated route table and delivered to the attachment B for VPC B. Now, this configuration has a couple of trade-offs. On the pro side, it's very simple to configure. It's an attachment and some route table configuration in VPC. The trade-off is that the transit gateway will prefer keeping packets in the same availability zone. So if a packet is transmitted from a VPC instance in availability zone A, the packet will be delivered to the NAT gateway in the corresponding availability zone in the outbound VPC. What does that mean? That means that because we have a statically defined default route in our subnet route tables in the outbound VPC subnet, if there is a challenge or an issue with that particular NAT gateway or that NAT instance, you will need to intervene to redirect the traffic, either manually or through automated scripting. There's another approach that you can take. Oh, one more thing I should have mentioned. I have a black hole route here that I didn't speak to before. The reason for this black hole route is that in this case, I do not want VPC A and B to talk to one another. It is possible, if I don't have this black hole route, for traffic from VPC-B to make its way to VPC-A. The inbound traffic will have a 100.64 address because it will in fact be NATed, and it will be returned because of the route table entry you see in the outbound VPC for 10/8. So just to note, if you wish to prevent instances from talking to one another in this configuration, using the NATs, this black hole route is required. All right, so another way that you can resolve, or another way that you can configure this for centralized NAT is to take advantage of equal cost multipath over VPN, which is available to you with AWS site-to-site VPN on the Transit Gateway. With Transit Gateway, we give you the ability to horizontally scale your VPN using ECMP. We've tested up to 50 gigabit, and we're sure that you can go higher than that if you need it. With this configuration, I can spin up as many instances as I like. The VPN terminates on those instances. The instances announce a default prefix, which is installed into the VPC route table. VPC-A and VPC-B, their route information is propagated into the outbound route table. And otherwise, this looks very similar to what we saw before. So 10.2.0.20 puts a packet out. It's received by the implicit router. Next hop is the TGW. It's received by the TGW. A lookup is done in the associated route table. Next hop is the VPN attachment, and at this point, the traffic is flow hashed across the ECMP links. The NAT instance will make routing decisions internally. When it determines that it needs to go out to the internet gateway, it will put it back onto the subnet within the VPC. That packet will go through the implicit router and onto the internet gateway. Return traffic, same as before, received by the NAT, which is done as source NAT, so it's going back to the same one. The 10.2.0.20 address is reset as the destination. Packets received by Transit Gateway. The associated route table is consulted, and the packet is forwarded to the attachment for VPC-B. So again, trade-offs here. This takes a little bit more effort to set up. You have no bandwidth throughput limitations, at least not theoretical bandwidth throughput limitations. In this one, you can continue to scale your NAT instances. In the prior example, the attachments will burst up to 50 gigabits per second. In this one, you could continue to scale horizontally. The challenge with this one, however, is I mentioned that ECMP is flow hashing the connections. So if there is a change in the configuration of the edges, right, the number of VPN attachments that we have, then your flow could be rehashed. If you have a stateful firewalling capability, that'll likely cause a connection reset. Let's look at an ingress use case. So we've got our VPC on the left. It's attached to a VPC route domain. We have our edge VPC on the right, again, using the VPN ECMP approach. A's routes are propagated to the edge route domain. The instances on the right, they propagate their routes to the VPC route domain. So let's see what it looks like for traffic that's coming into the environment. For fun, we'll put an elastic load balancing load balancer on the front of it to load balance the packets across the front ends. Packet comes in to the NAT instance. The target workload's determined. That instance then makes a change for the target, right? The destination address to, let's say, 10.1.0.10, and resets itself to source NAT with its 100.64 address. That packet is sent down the VPN tunnel. When it's received by the AWS Transit Gateway, the packet is assessed against the associated route table for that attachment. The associated route table says the next hop is the attachment for VPC-A. The packet's delivered. When 10.1.0.10 wants to return the packet, sends it to the implicit router. VPC route table is consulted. 100.64, remember that was the source NAT address, is the next hop to the Transit Gateway. Transit Gateway has a route to the VPN. It's delivered back to the source NAT and onwards to the Internet Gateway. One last use case, and I'll just forewarn you that when you think I'm done, I'm only halfway. So hold on. So we're going to do VPC to VPC inspection. So 10.2.0.20 wants to talk to 10.1.0.10. The configuration is very similar to what we did before for the centralized VPC using VPN, so I won't go over the whole configuration again. But let's watch how the packet will flow here, keeping in mind that I've taken away the black hole route. So 10.2.0.20 originates the packet, goes to the implicit router on the subnet, route table lookup occurs. 10/8 is available via the Transit Gateway. When it's received through the attachment, route lookup, and the associated route table, default route points to the VPN attachments. In this case, the VPN attachments are receiving the routes for these VPC subnets. So I mentioned earlier that in the case of a VPN attachment, the VPNs will receive over BGP the routes in the associated route table. So if you notice, the inline VPC route table only has a default gateway route, and that's so that these instances can actually reach out to the public IPs that terminate the site-to-site VPN. But the actual routing, the 10.1 and 10.2 addresses, are known to the instance route table because it's participating in BGP. And the VPC route table for the inline VPC does not actually need that route data. So the packet's gone through that NAT instance, it's been returned. The inbound packet, remember, is going to 10.1.0.10, but at this point it's been source NATed, so it looks like it's coming from 100.64. When it's received by the Transit Gateway, the associated route table is consulted, the packet's forwarded on to attachment B. I'm halfway. So now the 10.1.0.10 instance is going to send a response to 10.2.20. And I think you know how this goes at this point. The packet's forwarded. The VPC subnet has a route to 10.64 pointing to the Transit Gateway. The Transit Gateway has a route pointing to the the VPN attachments. In the VPN, that source NAT is reversed, passed back to the Transit Gateway. 10.2 route exists and points to the attachment for VPC-B. So let me reiterate the thing that I said at the beginning of the session. All of these things work, and you can do them. Talk to your SA before deciding you need to. So let's look at a reference architecture. We talked about flat and segmented common use cases. We've also talked about how to address traffic outbound and inbound from the internet, and how you can do inline services for both east-west and north-south. If you want to tie together Transit Gateway in multiple regions, you have a couple of options. Well, you have one option at the moment, which is to use our Transit VPC pattern. So you have a hub, a set of VPN appliances that are participating with Transit Gateways to provide connectivity. Of course, if you're just connecting two VPCs, you can use inter-region peering with VPC. AWS Transit Gateway does have inter-region support coming soon. Now, the last thing that I wanted to share with you is a pattern that we've seen start to emerge with customers. And I want to go through it largely because we're seeing some anti-patterns in how customers are trying to deliver this type of architecture. So we wanted to give it to you very specifically so you know what to do if you want to implement a similar architecture. What we're going to try and do here is have a shared services VPC where all of our key resources exist. VPC endpoints powered by private link, Route 53 resolver, connectivity is available to and from it, and through the VPN and Direct Connect gateway from our on-premises environment. So let's start to build this. Now, for this particular configuration, I tested this with a Session Manager. Session Manager, just if you don't know, is a fully managed AWS Systems Manager capability that allows you to manage Amazon EC2 instances through an interactive one-click based shell or through the AWS CLI. So Session Manager effectively provides you the secure and more importantly, auditable instance management without the need to open inbound ports or maintain bastions or rotate and maintain SSH keys. It's a very, very powerful capability. And it also works through VPC endpoints using private link. So you can have a completely isolated VPC and be able to get into instances using IAM authentication. So I'm going to use that as my VPC endpoint. So let's start to build this. So the first thing I need to do is I'm going to share my Transit Gateway with the other VPC instances. And I should note that the VPC instance for development and test are in their own isolated accounts. Production and the shared services VPC are in a common organization, and the AWS Transit Gateway was created by and effectively is owned by the shared services VPC. So I need to use AWS Resource Access Manager to share this Transit Gateway with the other VPCs. So I'll create a share. I'll define the shared resource, which is my Transit Gateway. I'll define the principals that I'm sharing it with. In this case, you see an account for development, an account for testing, and the organization that includes the production VPC. In each of those VPCs, I will accept, I should say in each of those accounts, I will accept the resource share, and that allows me then to create attachments to the Transit Gateway. So at this point, and I'm using a default configuration, single route table, single association, single propagation point, at this point I have connectivity between all 4 of these VPCs and my on-premises environment. Okay, the next thing I want to do is set up the VPC endpoints for Sessions Manager. There are 3 of them. So to do that, I will provision these VPC endpoints powered by Private Link in the Shared Services VPC. When you provision your VPC endpoint, you have this option, Enable Private DNS Name. And I want to spend a moment talking about this because this is where we're seeing a common anti-pattern. If you check this box, what will happen behind the scenes is AWS will create for you a Route 53 private hosted zone, and we will associate that with the Shared Services VPC. And the effect of that is that when you resolve the public DNS name for, let's say, ssm.useast2.amazonaws.com, you'll get back the private IP address. And that's the behavior that you want. But if Amazon has created that private hosted zone for you, you have no mechanism to share that with your other VPCs. So what we'll do instead is we will not check this. We will leave it as it is, and we'll get back after the creation an endpoint-specific DNS hostname for the VPC endpoint. Then we can create a private hosted zone at the apex, in this case, ssm.useast2.amazonaws.com, create an alias record at the apex pointing to that endpoint-specific hostname, and then using the AWS CLI or APIs, we can share that private hosted zone to the other accounts. Note that sharing of a private hosted zone between accounts outside of the account that is owning the private hosted zone can only be done via the CLI or the API, but it is possible. So please do not use Route 53 resolvers to talk to themselves to communicate zone information. So at this point, if a box in the development VPC wants to get the IP address for ssm useast2.amazonaws.com, it will query its .2 resolver. It will get back the private IP address, and it has network connectivity. It can get to it. Now, I also said that I wanted to enable connectivity to the on-premises environment. So what we'll do here is establish, using Route 53 resolver endpoints, the ability to resolve from our corporate infrastructure and resolve from our VPCs for the appropriate zones. So for example, I want the corporate infrastructure to be able to get to that SSM private endpoint, and I want the development account, for example, to be able to resolve corp.internal addresses. We'll use Route 53 resolver endpoints to do this. There are 2 types of resolver endpoints. There is an outbound resolver endpoint, which allows queries in the AWS cloud to be conditionally forwarded to an on-premises DNS server. And conversely, we also have the notion of an inbound Route 53 resolver endpoint that allows the on-premises environment to conditionally forward to AWS to get route resolution for things like private hosted zones. So that's all well and good. The corporate infrastructure has the ability now to resolve that SSM fully qualified domain name. It will get the internal IP address. It has the connectivity. And the shared services VPC can resolve corp.internal addresses. But at this moment, the development, testing, and production organizations cannot. They need access to that outbound endpoint. To do that, you'll again use AWS Resource Access Manager. And the Resource Access Manager will let you create an outbound rule, that you can then share with the other 3 VPCs. You accept that rule, and now when an instance in the development VPC wants to make a query to resolve corp.internal, it makes that request to its .2 DNS server. In the background, Route 53 resolver will make a query through the outbound endpoint to the on-premises environment, receive the information, and then return it to the instance in the development account. Please use this as a reference architecture, and I'll just say it again because we've seen it as a common anti-pattern. Please do not connect inbound and outbound endpoints to communicate zone information. We have the ability for you to share private hosted zones and for you to share outbound endpoints. Some parting thoughts for you. So as I'm wrapping up the session here, things to think about. The TGW provides customers a centralized place to simplify at scale VPC and on-premises connectivity. The TGW provides ECMP for VPN attachment types that allows you to scale your VPN connectivity horizontally. And the TGW provides you robust routing capabilities through the use of route domains. And as you've probably heard, the vast majority of our roadmap, more than 95% of it, comes from our customers. If you have input on how we can deliver additional benefits to you using the Transit Gateway, please let us know. We want to hear from you. I want to thank all of you for joining me, and I hope this session helps you better understand TGW, its capabilities, and the flexibility it affords. I'm happy to take questions out on the site afterwards. Enjoy the summit, and thanks for your time.